Hi and hello to everyone. In this video, we are going to see the basics of flip-flops. There are four types of flip-flops are there. They are the SR flip-flop, JK flip-flop, T flip-flop and D flip-flop. We will be seeing the logic diagram, the functional table and the characteristic equation of each flip-flop. Remember that flip-flops are used in the construction of sequential circuit. Go to the lecture. What is a flip-flop? Flip-flops are the storage element. Each flip-flop can store single bit of information. So if I have one flip-flop, I can store how much information? One bit of information. These are the types of flip-flop: SR, JK, T and D flip-flop. It is used in implementing a sequential circuit. What is a sequential circuit? Sequential circuit is the one whose output, sequential circuit is the one, I can say, whose output depends on present and past input. Okay, present and past input. Or else I can say past input, I can say, or else I can say past output. Okay, so example I can give for sequential circuit is your counters and registers. Because I am counting the number of students in the classroom, how I will start counting? I will counting from 1, 2, 3. What is the next count? After 3, I will be counting 4. Okay, after 3, I will be counting 4. That means the why I am counting 4 is because I am seeing a student, so I should count him 4 as well as the past student number is 3. Okay, so the present output depends on whose output depends on present input and past input or past output. Such circuits are called sequential circuit. Example, if I am counting the dates, which today is the day, I can say it's November 22. What is tomorrow? Tomorrow is November 23. Why it is November 23? Because tomorrow's sun is rising. It's a new day. We say it is 23. New day. So 23. Why it is 23? Depends on the past input. What is the past input? Past input is yesterday. That is November 22. Okay. So the next state or the output, present output depends on present input and past input, I can say, or past output also I can say. Such circuits are called sequential circuit. These sequential circuits are implemented by using flip-flops, right? And you know, this such circuit, example for sequence circuit, you can say counters. If I'm counting 1, 2, 3 number of students in the classroom, or I'm implementing or counting the values using a digital circuit, such circuits are called counters. And these registers, we know registers are nothing but registering, storage elements. Okay, if I say I'm having 8-bit register, that means I need 8 flip-flops to implement a 8-bit register. If I say it is 16-bit register, I can store 16-bit information. That means I need 16 flip-flops. Right? Let us start with the SR flip-flop. SR. S stands for set. S is for set. R is for reset. Okay, so this is called latch. First we will see what is S bar, R bar, latch. Then we will move into SR flip flop. Right here we can see two NAND gates are connected. Two NAND gates are connected. Okay, two NAND gates are connected, and the output of the first NAND gate is coming as the input of the second NAND gate, and the output of the second NAND gate is going as the input of the first NAND gate. I am saying the other input as S bar, the other input of the second NAND gate is R bar. And remember, in any flip-flop, output is always complement. Any flip-flop will have two outputs. The output is represented by Q. The other output is Q bar. What is the meaning? Q can be 0 or 1. Similarly, Q bar can be 0 or 1. If Q is 0, Q bar is 1. If Q is 1, Q bar is 0. It is always complement. Both cannot be 0. Similarly, both cannot be 1. Okay, what about S bar, R bar? These are the two inputs. Two inputs can be 0, 0, 0, 1, 1, 0 or 1, 1. Okay, that's why I have taken the four circuits. For each of the combination of each of the combination of input, I will be checking the outputs. Right? Okay, here the present input is represented by n. N is the present input. N plus 1 is the next, sorry, present state I can say, not present input, present state. N is the present state. N plus 1 is the next state. Right? Now let us start with the first flip flop. Let me say the next state input. Input I'm giving as in some other color. Let me use red color. Input I'm giving as 0 0. Okay. We know in a NAND gate, right? What is the output of Q? Q is nothing but S bar, Q bar. See, S bar, Q bar, NAND operation is your Q. Similarly, Q and R bar, NAND operation is your Q bar. Okay, so in a NAND gate, when any one of the input is 0, okay, if you look at the NAND gate, I have already explained a basic gate video lecture. You can watch that video. In a NAND gate, when one of the input is 0, definitely the output is 1. Similarly, when one of the input is 0, definitely the output is 1. Okay, if you look at this, both the outputs are trying to be 1 1. This is forbidden. We should not have such outputs because Q and Q bar should be complement. So when I give the input 0 and 0, both the outputs are trying to be 1. So I should not give S bar R bar as 0 0. Okay, so I will fill the table here. When S bar R bar as 0, I should not use. This is called forbidden or banned. I should not use this. Use the state. Okay. Next. What about the other inputs? Let me say S bar is 0, R bar is 1. So S bar is 0, R bar is 1. Okay, so NAND gate, when the input is 0, what about the output? When NAND gate, one of the input is 0 means output is definitely 1. 1. This 1 is coming here, 1 1, the output is 0. Right? We are not worried about the past states. We are not worried about the past states. See, I have mentioned here the states as Qn plus 1 and Qn plus 1 bar. Okay, what is the past state? Qn bar. Right? This Qn bar can be 0 or 1, this can be 1 or 0, whatever may be. If I give 0 and 1, definitely the output is 1. Because of 0, we have to start for an AND gate, we have to start with the analysis of 0. Okay, so 0 means definitely this 1 is fed back here, so 1 1 AND gate output is 0. So Q is 1, Q bar is 0, so I can write the output here as Q is 1, Q bar as 0. Okay, next let me go into the third input combination. S bar is 1, R bar is 0. S bar is 1, R bar is 0. Okay, as I said earlier, in an AND gate, we will start with the input 0. When the input is 0, definitely the output is 1. So this 1 is fed back here, 1 1, the output here is 0. Right? So we are not worried about the past values. Past value can be like, this can be 0 or 1, this can be 1 or 0, it can be anything. If I give the input 1 0, Q is 0, Q bar is 1. Okay, then we go into the last combination. Okay, when the S bar is 1, R bar is also 1. When both are 1, I cannot start the analysis, because for an AND gate I can start the analysis when where the input is 0 only I can start, right? So let me use some other color to say the past. Past means Qn equal to 0, Qn bar equal to 1. This is assuming, right? Let me assume the past values are Qn equal to 0, Qn bar equal to 1. Okay, now this 0 is fed here. NAND gate means I have to look for the 0. Since both the inputs are 1, I cannot start it. So I look at the past output. So 0 is coming here. So if it is here 0, if it is 0 means what happens? NAND gate, one of the input is 0 means What happens to the next state? Qn plus 1 bar. It is 1. Now this 1 is fed here. 1 1 output is 0. So Qn plus 1 is 0. So what we have understood, if the past value is Qn is 0, Qn bar is 1, the next value of Qn plus 1 is also 0, Qn plus 1 bar is equal to 1. Okay, this is one assumption. Let us make another assumption. It can be 6, need not to be always 0 and 1. Okay, it can be 1 or 0. We will check that case also. Right? That case I will write it here. Let us assume the past value as, I will use green color, past value as 1. Qn is 1. So Qn bar is 0. Qn bar is 0. Okay. So if for this case this 0 is fed here. So 0 1 as input. So the next state output, that is your Qn plus 1. Qn plus 1 is equal to 1. Okay, this 1 is coming here, so 1 1. So the next state output is Qn plus 1 bar is 0. Now we are going to make an important conclusion. What is the conclusion? Sir, if the next state is, if the past state is 0, when I give the input is 1 1, the next state is also 0. If the past state is 1, if I give the input 1 1, the next state is also 1. That means Qn plus 1 is equal to Qn when I give the input 1 1. That is the conclusion. Okay. This is for the example I have taken. I have taken the past state 0 1 as first example, 1 0 as second example. Whatever I will take, the next state is equal, Qn plus 1 is equal to Qnc. Qn plus 1 is equal to Qn. Qn plus 1 is equal to Qn. Similarly, Qn plus 1 bar is equal to Qn bar. Okay, similarly Qn plus 1 bar equal to Qn bar. Okay, so I can write the conclusion here as, what is the conclusion? Qn plus 1, when the input is S bar is 1, R bar is 1, I can conclude that it is equal to Qn. Similarly, for Qn bar it is Qn bar. Qn plus 1 bar it is Qn. This table is the functional table. This table is called functional table. Functional table of SR latch. We don't have any clock pulse. Okay, we need to use any clock pulse. That is why it is called, not called as flip flop. It is called as latch. Okay, right? This is called S bar R bar latch. Now we are going to convert this S bar R bar latch into SR flip flop. Okay, we'll see in the next slide. Okay, so what about this? This is what we have already seen. This is your S bar R bar latch. Okay, I can write it here as S bar R bar. What I have done here is I have made a NAND gate. One of the input NAND gate is clock. So when the clock is 0, what happens? When the clock is 0, NAND gate, both the inputs are 0. Both the inputs are 0 means here both the inputs are 1 1. 1 1 means what is the state? When the input is 1 1, for the S bar R bar, it is equal to memory. Memory means Qn plus 1 is equal to Qn. It is remembering. Next output is equal to past output. Okay, so I can conclude that when the clock is 0, whatever may be the SR values, SR value, if your clock is 0, S is 0, or can be 0, it can be 0 or 1, 1 0 or 1 1. Don't worry about that. When the clock is 0, definitely these two are 1 1 because of NAND gate. When both are 1 1, we have seen in the last slide, it is equal to the past values Qn bar. Right? Next, I am going to give clock as 1. Clock as 1, S R as 0 0. Right? So I am going to give clock as 1. Both are 0 0. 0 0 means what happens? NAND gate input 0 means this is 1. 0 means this is 1. Okay. I will write it here and then figure a bit 0 0. So it is 1 1. Okay, so S bar is 1, R bar is 1, right? So what is happening? We have seen in the past, we have seen in the last table, 1 1. 1 1 means memory. S bar is 1, R bar is 1 means Qn plus 1 equal to Qn, Qn bar plus 1, Q plus Qn plus 1 bar is equal to Qn bar. So this is memory. This is said as memory. Next, I will look for other combination. Clock is 1, S is 0, R is 1. Okay, so I can rub it off these things. S is 0, R is 1. Okay, now try to fill S bar, R bar. S is 0, clock is 1, so the S bar is 1. So this is 1. So when both the inputs are 1, what is R bar? This is 0. Look at the past table. When S bar is 1, R bar is 0. When S bar is 1, when S bar is 1, R bar is 0, it is 0, 1. It is 0, 1. Next, look, try for other combination. Clock is 1, S is 1, R is 0. I will rub the past values. Now I will make it as S is 1, R is 0. Right? So if both the inputs are 1, 1, what is the output? 0. When this is 1, this is 0. NAND gate, the output is 1. S bar is 0, R bar is 1. If you look at the past slide, S bar is 0, R bar is 1 means what happens? The output is 1, 0. Let us go into the last one. Both are 1, 1. Both are 1, 1. Okay, so I'm going to change this R. Right? When both the inputs are 1, 1, output is, this is 0. If this is both are 1, 1, the output is 0. Okay, in S bar, R bar, when both the inputs are S bar, R bar, and both the inputs are 0, 0, it is forbidden. We should not use that. Okay, so this is forbidden. Forbidden, or I can say other name for forbidden is, and you should not use it. Forbidden state, or else you can say banned. Right, now this is the functional table of the SR flip-flop. Right, I quickly easily understand that. You can see that when the clock is 0, when the clock is not there, nothing is going to change. Okay, I can rub the previous things, right? When the clock is not there, whatever may be the S and R, no problem for me. This is called don't care. The output is, next state output is equal to present state output. When the input is 1, it is going to act as memory. It is going to 0, 0. When the input is 0, 0, it is going to act as a memory. When the input is 0, 1, 0, 1 means what is the meaning? R is 1. R means reset. Reset means Q is 0. Q is 0 means Q bar is 1. Next is set is 1, R is 0. So set is 1. S is 1 means set is enabled. So Q is 1, Q bar is 0. 1 and 1, we should not use that, because both the outputs will be tried to be 1, 1. You should not use that. Okay, so this is the truth table or the functional table of the SR flip-flop. This is the symbol of SR flip-flop. Okay, here the input S and R is there, as well as we have the clock. Output is Q and Q bar. So this is the output. These are the inputs. Okay, so this is the symbol of SR flip-flop. Now we will see the next flip-flop, JK flip-flop. See, what is the drawback with the SR flip-flop is the last state. Last state is forbidden. So we have to avoid this state. We have to avoid this state. To avoid this state, we go into JK flip-flop. In JK flip-flop, if you observe closely, this is your SR flip-flop. So this is your S, this is your R. This is your S, this is your R. And if you take this Q and connect it to a AND gate and give K, right, and connect it this to R. So I can write it here. This is your R, this is your S. Similarly, Q bar is taken and with the J, it is connected to S. If you look at this you can see this clearly. This is your SR. So I made a block of SR flip-flop. I have taken Q bar and with the J connected to S. Similarly, I have taken Q and with the K connected to R. Okay, this entire thing is your JK flip-flop. Right? JK flip-flop, only difference is the last state. What is the last condition? When both the inputs are 1 and 1, it should not be used in SR flip-flop. Okay, but in JK flip-flop it will be toggled. You will see how it is. Right? Others are the same. When the clock is 0, J and K can be any value. It will act as a memory. Qn plus 1 is equal to Qn bar. It is acting as a memory. When the clock is 1, both the inputs are 0. It is going to be that also a memory. Very same as the SR flip-flop. If it is 1, J is 1, sorry, J is 0, K is 1 means reset. 0, 1. Clock is 1, J is 1, K is 0 means set. So it is 1, 0. The last one, this is the difference between SR and JK. When both the inputs are 1, 1, I should not use SR flip-flop, but here it will be complement. Qn bar, Qn. If you observe this, what is the meaning is this all is the bracket I have mentioned here, this all similar to SR flip-flop. Only the last line is different from the SR flip-flop. When the input is 1 and 1, next state Qn plus 1 is equal to the past state complement Qn bar. Similarly, Qn plus 1 bar is equal to Qn. Now we will write the equation for Qn plus 1. Okay, what is Qn plus 1? Leave the first line. First line we definitely will be using clock. Okay, we can ignore the first line. The other four lines, other four combinations, we are going to write Qn plus 1. Right? What is Qn plus 1? Qn plus 1 is equal to J0 K0. So J bar K bar Qn plus, when it is 1, J K bar, J into K bar plus JK, both are 1 1 means JK, we are having Qn bar. This should be Qn bar. You get the green color. It should be equal to green color. Or else, if you observe this expression, Qn plus 1 is equal to J Qn bar plus K bar Qn. J Qn bar plus K bar Qn. Right? You can check it. Right, we check it. What can I check now? Let me say J is 0, K is 0. J is 0, K is 0 means J0, this is 0, K is 0 means 0 bar is 1. 1 into Qn, Qn. So Qn plus 1 is equal to Qn. Qn plus 1 equal to Qn. When J is 0, K is 0. Check for the other combination. J is 0, K is 1. J0 means this is 0, K is 1 means 1 bar 0. So 0 plus 0, everything is 0. So the output is 0. Next is J is 1, K is 0, J is 1, 1 means 1 into Q bar, K is 0 means 0 bar is 1, so Qn bar plus Q, Qn bar plus Q is always 1. Last case, 1, 1, J is 1, K is 1, 1 bar is 0, so this term becomes 0, J is 1, 1 into Qn bar. Okay, so I can fill the Qn plus 1 by with this expression or this expression. This equation is called characteristic equation. Right. Next, we will see the other flip flop called T flip flop. What is called T flip flop? T flip flop is nothing but a toggle flip flop. Toggle. That is why it is called T flip flop. What I have done here is I have interconnected J and K together. J and K together. J and K together means what happens? T is 0 means both the inputs are 0. T is 1 means J and K both are 1. Okay, so let us fill now. When T is 0, when T is 0, both J and K are 0 means I can refer the previous slide. J and K is 0 means it is going to act as a memory. See, note down, this is memory, I forgot to write. This is toggle. Write it well. This is memory, this is toggle. Okay. So when both are 0, 0, if I give T as 0, both J, because they are interconnected, right? Both are 0, it is going to act as Qn plus 1 is equal to Qn. That is memory. Similarly, when I give T as 1, both the inputs are 1, 1. 1, 1 means you can refer the past slide. When both the inputs are 1, 1, it is going to act as a Qn plus 1 is equal to Qn bar. Qn plus 1 equal to Qn bar. So it is Qn bar. That is toggle. Okay, so simple. If I give the input 0, output will next state output Qn plus 1 is equal to Qn. If I give the input 1, next state output will be equal to complement of the past output. Right? So this can be characteristic equation given as T XOR with Q. So T Q bar, I can write Qn, that's the correct way to write. T XOR with past value of the output. So XOR I have expanded. Using this expression also, you can fill this table. This equation is called characteristic equation because this equation decides the output. How the output depends on the input and past output. Okay, this is called sequential circuit. Okay, output depends on present input as well as past output. Right. So if you look at this, so what we have done here is we have used these two states, this line and the last one, both are 0, both are 1. So if I want to use the 0, 1 and 1, 0, what I have to do? I connect between J and K a NOT gate. That is your D flip-flop. Between J and K, I connect a NOT gate. If D is 0, J is 0, K is 1. Okay, J is 0, K is 1. Right? So when J is 0, K is 1, J is 0, K is 1, it is Qn plus 1 is 0, Qn plus 1 bar is 1. So I can write the output as 0, 1. When D is 0, next output is 0. Similarly, I use some other color for the next combination. When D is 1, J is 1, K is 0. When the input is 1, 0, output is 1, 0. We can see the JK flip-flop. When the input is 1, 0, output is Qn plus 1 is 1, Qn plus 1 bar is 0. So when the input is 1, output is 1. Okay, it's very simple. Right? So that is why if I need the output as 0, I have to give the input 0. If I need the output 1, the input is 1. Or if I give the input 1, output is 1. Okay, so output is equal to present input. That is why D flip-flop is nothing but just a delay. Input is delayed. It's called delay flip-flop. Or it is also called transparent. Whatever I give as input, that will be coming to the output. Transparent flip-flop. Okay, this is your D flip-flop. T flip-flop is your toggle flip-flop. I have written that, right? So don't confuse with T stands for D flip-flop. T transparent flip-flop, okay, is the same as the D flip-flop, or also it's called as delay flip-flop. Now what about the characteristic equation? It is very straightforward. Next state output is equal to present input D. This is the characteristic equation. Okay, I hope you understood about the basics of flip-flop. Using this flip-flop, we can construct a sequential circuit such as counters, registers. In counters, there are so many types. They are called synchronous counter, asynchronous counters. Okay, those things, if needed, I will be posting those videos. Thanks for listening. Any doubts, please ask in the comment section. Jai Hind.